Now, I will show you in this video how we will proceed to obtain the Lagrange equations. This is what I found in my previous work. The Lagrangian, I was able to break the Lagrangian into two parts: the Lagrangian of the center of mass and the Lagrangian relative to the center of mass. Now, the part that corresponded to the center of mass Lagrangian was simply 1/2 the total mass of the system times the speed of the center of mass squared. And then I had a kinetic energy term that depended on the reduced mass. Let's make some notes. So this here, this is the reduced mass. This is the speed with respect of the speed of the speed of 2 with respect to object 1, and this is the potential energy of the system. And this is the total mass, or the mass of the center of mass. Let's say total. And this here is the speed of the center of mass. Now the form, okay, I'm gonna write what the Lagrangian equations look like. So it's the partial of L with respect to a generalized coordinate, and that is equal to d over dt of the partial of the Lagrangian with respect to q dot, the generalized velocity. Now here, okay, I want to see what this quantity depends on. So the dependency of the first part, the Lagrangian part of the center of mass, this depends on the speed squared. Now this the speed is always dependent on the x component of velocity, the y component of velocity, and the z component of velocity. So if you have x, y, z of the center of mass and you take the time derivatives, then this will be the x component of velocity, the y component of velocity, the z component of velocity, and for all of these I'm referring to the center of mass. Okay. Now, if you take a look here on the left side, if I do the partial of L, where the Lagrangian is this, the whole thing, with respect to x of the center of mass, I will find that to be 0, because the Lagrangian part of the center of mass only depends on the kinetic energy, which depends on the speed, which depends on x dot, y dot, and z dot for the center of mass. There is no dependency of L of the center of mass with respect to x, y, z of the center of mass. L is independent of that. So I can also say the partial of L with respect to y of the center of mass, and this is equal to the partial of L with respect to z of the center of mass. Now, because the left side is 0, this means that d over dt of this quantity for x dot, y dot, and z dot will also be 0. So let's see what we get. d over dt of the partial of L with respect to x dot of the center of mass will be 0. Now, I want to remind you the speed, the speed of the center of mass, what is that? So let's see, v com squared, this will be the square root squared, which will cancel out, and then I have vx squared of the center of mass, that is vy of the center of mass squared, so this is of the center of mass, plus the same thing for vz squared of the center of mass. Now, if I take the partial of this with respect to vx or x dot, the same thing, then this will give me simply 2 times vx, and the 2 with the 1/2 will cancel out. So d over dt, the partial of L with respect to Vx of the center of mass will give me m Vx of the center of mass, and that should be 0. And then this will give me m Ax of the center of mass is 0. Now, if I do the same thing, if for y dot and z dot, I'm gonna get m Ay of the center of mass is 0. That should be uppercase M. All of these are uppercase. And if I want, I can write it as a vector. MA of the COM should be 0, or since the acceleration is the second derivative of the position vector, this, which is telling me that the center of mass of this system is moving with 0 acceleration, or in other words, with constant velocity. So this is what I get from the center of mass part of the Lagrangian, that the acceleration is 0 of the center of mass. Now, I also have the second part of the Lagrangian, the one that depends on the relative motion of the system with respect to object 1.